All right. So we're starting chapter 4. Chapter 4 is graphing and optimization. Section 1 is first derivatives and graphs. The interesting thing about chapter 4 is I'm going to give you an equation and you're going to talk about it. It's about the original, but how we talk about it, we have to take derivatives, we're going to work on it, we're going to look at some interesting things, but really all we're doing is analyzing a graph and looking for the highs and lows and what that means, but we use calculus derivatives to do it, okay? So the first derivative is associated with the slope of the graph of a function at a certain point. It is reasonable to expect that the first derivative is also related to other properties of the graph. In this section, we examine how information about the first derivative reveals insights into the shape of a graph of the function. In particular, we study methods for finding absolute maximum, minimums, valuable information used to guide decision in manufacturing, pharmaceuticals, marketing, and other areas. So bottom line, we've taken a derivative. We've learned product rule, quotient rule, chain rule, special cases. We've learned all this stuff on taking a derivative. Now we're going to use it. We're going to use the derivative to find maximums and minimums. Like you want to maximize revenue, but you want to minimize costs. Things like that. But we've already learned the derivative part. Now we're going to learn how to use it to analyze. So sign charts are used to extensively in this chapter. It is suggested that you review the terminology in section 2.3. In the next slide, we talk about using a sign chart. Now, I'm not a huge fan of sign charts. I'll be completely honest about that. I'm going to show them to you. We'll talk about them. If it helps you, fantastic. I like looking at the graph. That's how I like to do things. So let's start out by taking off your calculator. And in our calculator, we're going to put this equation in a standard window. Go to our calculator. Okay, so we go to our calculators. We go to Y1. Get rid of anything you have in there. And in Y1, we're going to put the original function. The original function is x raised to the third minus 3x. X raised to the third minus 3x. So I'm going to follow the notes, but I'm also going to jump in and out a little bit. Okay? Make sure all your plots are off. Make sure all your plots are off, plot 1, plot 2, plot 3, everything's off. And then, just to make sure we have a nice window, hit zoom 6. Zoom 6. Now, what are we going to do this whole chapter? Basically, here's the original function. See how it goes up, gets to a high point, then it goes down, gets to a low point, and then it goes up? This is the original. We can find these high points and low points and these changes using derivatives. But it's all using derivatives to talk about the original. Using the derivatives to talk about the original. So, going back to the notes. If we take the derivative, so what's the derivative of x cubed? 3x squared. What's the derivative of 3x? 3. So we take the derivative. We can factor that as into 3x plus 1, x minus 1. And if we take the derivative and solve this, set it equal to 0, take the derivative, set it equal to 0, what number makes this 0? -1. And what number makes this 0? 1. So what did I do? I took the derivative and I set it equal to 0. So let's kind of work that out. So we're trying to learn about the original. The original is x cubed minus 3x. To learn about the original, we did a quick picture of that. A quick picture is that it goes up, it goes down, and it goes up again. That was our quick little picture we did. How can I learn more about that original? How can I learn more about the original? Well, if we take the derivative of that function, what's the derivative of x cubed? 3x squared. And what's the derivative of negative 3x? Negative 3. We take the derivative. We take that derivative, set it equal to 0. And when we solve, algebra, set each piece equal to 0. You get x equals 1, x equals -1. So quick review. What do? We're trying to talk about the original. And to talk about the original, we take the first derivative, set it equal to 0, and solve. Now those points, 1 and -1, those points, 1 and -1, those are really unique special points. They help us understand the original. So if I go to my calculator, and I'll show you a little trick. Hit second trace, hit number 1 for value, and the two numbers we're going to look at are -1. Well, if I type in -1, hey, where is that? That's at a high point. And if I hit 1, enter, where's that? That's a low point. So by taking the derivative, setting it equal to 0, it helps me find the highs and lows of the original. Make sense? That's chapter 4. That, in a nutshell, is what we'll be doing in chapter 4. Okay? So back to the notes part. What we're learning first of all is that at -1 and at 1, that gives us the high and the low point. Everybody got that? But if I plug in numbers here, it's going to be positive because it's increasing. If I plug in numbers here, it's going to be negative because it's decreasing. And if I plug in numbers from 1 on, it's going to be positive because it's increasing. So what does that mean? If I go to my calculator, and let's change y1 to the derivative. The derivative is 3x squared minus 3. So in y1, we put the derivative 3x squared minus 3. And remember my 2 points were -1 and 0. Go to the table, second graph. Give me some numbers that are less than -1. Numbers that are less than -1. -4. If you type in -4, you're going to get a positive result. What does that mean? It means it's going up. Another number, less than -1. -2. It's a positive number. It's increasing. -3. Anything less than -1 in the derivative will give me a positive result. That means it's increasing. Okay? So on my picture, anytime you plug a number less than -1 into the derivative, it's going to be positive to show it's increasing. Okay? Give me a number between -1 and 1. Give me a number between -1 and 1. 0. If I type in a number between -1 and 1, I'm going to get a negative result. 0.5. -0.5. That's telling me, if you plug into the derivative, that's where the graph is decreasing. Now, what's a number bigger than 1? 2, positive. 3, positive. 4, positive. Those are anything after 1, plug it into the derivative, it's where the graph is increasing. Now, you're probably saying, well, that's kind of nice. And I agree. It's not earth-shattering. The part that I really want you to focus on is that -1 and 1 were our highs and lows. How do we get that? First derivative, set it equal to 0 and solve. You need to know how to take a derivative, and you need to know your algebra. Okay? The sign chart is to help you saying, if you plug into the derivative, anything less than -1, you'll get positive results, which means it's increasing. Anything between -1 and 1, negative results decreasing. Anything after 1, increasing. So that's what the sign chart is saying. Okay? But what I want you to know, which we'll get to in a little, I like in a handful of slides, is that take the first derivative, set equal to 0, and solve. You'll find some potential highs and lows. Okay? So that's what the sign chart's showing you. If you plug into the derivative and you get a number greater than 0, that's when it's increasing. If you plug into the derivative and it's less than 0, that's where the graph is decreasing. Okay? So if I had 8x minus x squared, I want you to practice. Take the derivative, set it equal to 0, and solve. Find the numbers. Those are called critical values. We'll show that soon. But let's practice the take the derivative, set it equal to 0, and solve. Number 1, you need to know how to take a derivative. Number 2, you need the algebra. Okay? So take the derivative, set it equal to 0, and solve. No calculator, on a piece of paper. Take the derivative of 8x minus x squared, set it equal to 0, do the algebra. That's going to be our issues, is the algebra and the derivative, which we should all be amazing at. So again, the side chart is good. Understand it's showing increasing and decreasing. That's what we want to get. Okay, so again, this is our original 8x minus x squared. What's the derivative of that? 8 minus 2x. So we take the derivative. If I want to find those potential highs or lows, we take that, set it equal to 0. And again, if we're having problems with derivatives, that's going to be a problem for it. This is a basic derivative, right? Straightforward, nothing special. If I solve for this, add 2x, 8 equals 2x, divide by 2, what do we get? X equals 4. Okay? So bottom line, something special is going on about the original at 4. Something special is going on at the original at 4. So let's graph it. And what are we graphing? We're graphing the original. We're graphing the original. All of this is about how the original is changing. All of this is about how the original is changing. So we go to our calculator. We type in 8x minus x squared. And then we'll leave it in the same window. We'll leave it in the same window, which is negative 10, 10, negative 10, 10. Graph. Oh, what's the problem? I don't see it, right? I need to see more what? So let's talk about window. I need more x min, x max, y min, y max. Y max. So let's go to window. Let's change y max to 20. Window, change y max to 20. Hit graph. See if we see it now. Okay, now we see it. Now I want you to put your cursor on 4. How do you get your cursor on 4 again? Second trace. Number 1 for value. Choose 4. Second trace. Number 1 for value. Choose 4. Second trace. Number 1 for value. Choose 4. So again, let me be very clear. I keep saying this because this is where people get confused. We did a graph of the original or the derivative? The original. It's a graph of the original. How did I find that high point? Take the derivative, set it equal to 0, and solve. Okay? Now, they want you to teach, well, going by the slides, when will the derivative give you positive results? When will the derivative give you positive results is when the graph is increasing. So if I plug in a number less than 4 into the derivative, any number less than 4 in the derivative will give you positive results or negative results. Positive results, because that's where it's increasing. So how can I tell if a graph is increasing or not? Without the picture, look at the derivative, plug in a number. If it's positive, it's increasing there. If it's negative, it's decreasing.
You said any number less than 4.
Yep.
Like negative 2.
Yeah. So if you plug in -2 into the derivative, you'll get a positive number. Positive numbers in the derivative means that's where it's increasing. If you plug a number greater than 4 into the derivative, what will happen?
Oh, I see what you mean by it. Okay.
So positive results in the derivative means it's increasing.
Yeah.
Negative results in the derivative means it's decreasing. Oh, because I'm going to show you plugging stuff in. Okay? So again, this is a picture of the original. Increasing, decreasing. So if I want to show that, go to y equals, get rid of the original. Let's plug in the derivative. The derivative is 8 minus 2x. So what's the magic number? 4. Right? Now I have the derivative. If I go to the table, any number less than 4, 2, 3, 3.5, 1, 0, all of those are giving you positive results. Positive results in the derivative means that's where the original is increasing. Any number after 4, 5, 6, 7, 8, 9, all those are giving you negatives, which means that's where the original is decreasing. Okay? That's what the derivative does. But the most important part is how did I get that 4? Take the derivative, set it equal to 0, and solve. That's the most important part. This other stuff is important, right? 4 is the magic number. When is it increasing? Anything less than 4. When is it decreasing? Anything after 4. Okay? So it's increasing when it's less than 4. It's decreasing after 4. The magic is finding that number 4. That's where everything changes. Okay? And then the last question says, sketch a graph of f for any horizontal tangent lines. Well, where is the top point? At what number? Where's the top point? At 4. At 4. So where is there a horizontal line? It would be at 4. It would be at 4. And a graph of a horizontal line would be y equals 4. Now, why is that important? Remember slope? Going upward, slope is positive. Going downward, slope is negative. What's the slope of a horizontal line? 0. That's when it's not going up. That's when it's not going down. Okay? So, bottom line, how do you find that 4? Then you can talk about what happens before and after. X equals 4. Sorry. Y.
Wait, what?
Graph of the horizontal line. Y equals, well,
What if we y equals 16?
yes, you're right. Y equals 16, and they're saying it's at 4. That's the most important part. So the graph would be, graph of this line is y equals 16. Thank you, and it happens at 4.
You said y equals 4.
Yeah. It happens at 4, but the graph is y equals 16. Thank you. X equals 4 is where graph is y. Now, bottom line, critical numbers. How do you find the critical numbers? It's where the derivative equals 0. That's where we can find these highs and lows. The sign chart just helps you for increasing and decreasing. So here's your first one. We have f of x equals 1 plus x cubed. Find the critical numbers. How do you find the critical numbers? What do? Take the derivative, set it equal to 0, and solve. Take the derivative, set it equal to 0, and solve. So we're talking about the original, and so we take the derivative. What's the derivative of 1? 0. What's the derivative of x cubed? 3x squared. We set that equal to 0. Divide by 3, x equals 0, x equals 0. So we have a critical number at 0. So how do you find a critical number? Take the derivative, set equal to 0, and solve. Now, let me explain to you what a critical number is. A critical number is where it may be a high point or a low point. Okay? It doesn't have to be, but it could be one. Okay? So we're going to go look at the graph at 0 and see if it's a high point or a low point. We're going to graph to see if it's a high point or a low point. The sign chart is a way to do it without graphing. Okay? Without graphing. So let me show you the sign chart way first. The sign chart way is to go to the calculator, plug in the derivative. What's the derivative? 3x squared. Now, I'm going to plug in numbers to 3x squared. I'm going to go, let's say, -5. Positive result. I'm plugging into the derivative. That's where the graph is increasing or decreasing. Increasing. -4. Increasing. -3. Increasing. -2. Increasing. -1. Increasing. Then we get to 0. 0 is our special number, right? Our critical number. At 0, it's 0. It's neither increasing nor decreasing. So anything below 0, it's going up. Okay. What happens afterwards? 1, still increasing. 2, still increasing. 3, still increasing. 4, still increasing. 5, still increasing. So basically, this graph, I know 0 is an important point. Before 0, it's going up. It gets to 0, it stops. And then what happens after 0? It keeps on going up. So if it goes up and keeps on going up, will it be a high point, a low point, or neither? Neither one. So the sign chart is a way to do it without graphing. If it goes up and keeps on going up, it's not a high or low. If it goes up and goes down, up and down, then you have a high point. If it goes down, then up, then you have a low point. Does that make sense? But for me, that's great, that's wonderful. I'd rather just see it. I'd rather go to y equals, type in the original, 1 plus x raised to the third. Now, what was the critical number? 0. So we need to see 0. So let's just do zoom 6. Let's do a standard window. We'll get better with windows later. But now I look at the original. I know what number to go look at. 0. Is that a high point or a low point? Is that a max or a min? Max would be top of the mountain. Min would be the bottom of the mountain. Is this a max or min? It's neither. Why? It goes up and keeps on going up. But that's the point I wanted to look at to check. Remember I said it may be a max or a min? Doesn't have to be. In this case, it isn't. Okay? So, if you use the sign chart, plug into the derivative, it's positive, 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 get to 0. After that, it's positive, positive, positive. It's not a max or a min. It's just increasing the entire time. But 0 is a critical point. Okay? Let's get a little harder. Now, let's really see how our derivatives are doing. Let's say we had 1 minus x raised to the 1/3. That's the original. Find the derivative, set it equal to 0, and solve. Find the original, got it. Find the derivative, set it equal to 0. Find the derivative, set it equal to 0. And again, it goes back to derivatives and algebra. So let's take the derivative. This one is going to be product rule, quotient rule, chain rule. What's this going to be? Chain rule. So the 1/3 goes in front. The inside stays the same. The 1/3 becomes negative 2/3 times the derivative of the inside is derivative of 1 is 0. Derivative of negative 1x is negative 1. Again, everything builds from test to test. We've gone over chain rule. Now we have to use chain rule to take the derivative. And then the algebra. This is where people get stuck. And sometimes you'll intimidate yourself when it's really not that bad. This is why I spend a lot of time simplifying. Negative 1 times negative 1/3 of 1/3 is negative 1/3. I'm going to move all that to the bottom and make that a positive 2/3. I'm going to set it equal to 0 and solve. Now, you're sitting here saying, ooh, that's a really hard algebra problem. That looks like a really hard algebra problem. And I'm going to make it very simple, just like that. All I have to do is figure out what will make this 0. And it seems like we have a problem, right? If I did proportion cross multiply, that would be 0, that's gone. The only thing I can think of, which is not the answer, but I can think of is number 1, it doesn't solve. The reason why it doesn't solve is if I made a proportion, that times that is 0, x is gone, nothing to score. So in this case, there's no solution. But I am noticing something. What would make this 0? What would make the 1 minus x raised to the 2/3 0? 1. So I bet something weird is going on at 1. I bet something weird is going on at 1. So I'm going to add to what I just said. To find those special critical points, you take the derivative, set equal to 0. Yep, that's true. Now I'm going to add, we're also going to look for anything weird. Anything that makes the derivative undefined. Anything that makes the derivative undefined. And what would make the derivative undefined? 1. So when we're looking for those critical points, those highs and lows, to find those possible maxes and mins, we're going to take the derivative, set equal to 0, step 1. Step 2, we're also going to see if there's anything that makes the derivative undefined. And in this case, what makes the derivative undefined? 1. Okay? Take the derivative. There's a problem at 1. And so there, let's look at the graph at 1 and see what we get. So if I go to the calculator, let's type in our original. We're going to keep it a 10 by 10 by 10 by 10. So you can hit zoom 6 or just hit graph. And let's see what happens at 1. So the graph is decreasing, 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 decreasing. When it gets to 1, it flattens out. And then it still decreases, decreases, decreases. Something interesting happened at 1, but did this form a maximum or did this form a minimum? No. Decreasing to decreasing doesn't form. We're going to be looking for increasing and then decreases. That would be a max. Decreases, then increases. That would be a minimum. In this case, there's no max or minimum. Okay? So what's the big takeaways? We're looking at the original, looking for maxes and mins. How do you do it? Take the derivative, set equal to 0 and solve, and take the derivative and see if there's anything that would make it undefined, any dividing by zeros. Okay? So all of that set up, and again here it's negative and then it decreases some more. So we don't have any, it's undefined at 1, but we don't have any maxes or mins. It's decreasing the entire time. Okay? So for this one, f of x equals 1 over x minus 2. Let's practice again. I'm going to help you with this one, because this one may not be as obvious. So for this one, here's our original. Here's our original. And we should already look at it. And do you see anything interesting about this one before we even move on? Look at the original. What do we know about graphs? What do we have and where? At 2, what do we have? What's it called? It's undefined at 2. What do we have there? What's it called? It's a critical number, but what's it called? Remember from the last chapters? What makes the original undefined is 2, we have a vertical asymptote there. Okay? So something's going on at 2, but still, we're going to go through our steps. We're going to find the derivative, but before we find the derivative, I would have to do quotient rule. Quotient rule takes a long time. I actually like chain rule. So the question is, can I rewrite this so I'll be doing chain rule, which is a little bit shorter? And the answer is yes, I can. If I call all of this raised to the 1, so if I rewrite it as 1 over x minus 2 raised to the 1, I could rewrite that as x minus 2 raised to the negative. Okay? So with that little change, rewriting 1 over x minus 2 to x minus 2 raised to the negative 1, I want you to take the derivative and then stop. And we can take the derivative using chain rule. We can take the derivative using chain rule. So everything builds, derivatives, prodigal, quotient, chain rule, special cases. All of those are fair game. Okay? If we take the derivative, the negative 1 goes to the front, inside stays the same, x minus 2, subtract 1, the exponent is negative 2, times the derivative of the inside. What's the derivative of 1x? And the derivative of negative 2? 0. And if I clean this up, we get negative 1 over x minus 2 squared. Okay? The bottom line, we take the derivative. We take that derivative, set it equal to 0. If I take that derivative and set it equal to 0, it will not work. If I make a proportion 0 over 1, cross multiply, the x and the 0 turns into 0. There's no x. There's nothing to solve for. So this would be no solution, can't solve, no answer. So is there a number that makes it equal to 0? No. But the other thing I'm going to check is looking at the derivative, what number would make this undefined? 2. So as far as critical numbers, I'm going to go check out 2. I'm going to see what's going on in 2. Now, they're not calling it a critical number, but I'm going to say it is critical. It's important. It's a number we need to go check out. They show it later. I like to show it. So if I go to my calculator, let's graph the original. 1 divided by parenthesis x minus 2. Parentheses do matter. Be careful. Parentheses do matter. We know something's going on at 2. We know something's going on at 2. So if I hit graph, let's see what's going on at 2, and you've already figured it out. It is a vertical asymptote there. So before negative 2, it's decreasing. And after negative 2, it's decreasing. So even though 2 is not a critical number, but it's important because it's something we have to look at, does it produce a max or does it produce a min? No. It's actually a vertical asymptote. There is something going on. There is something going on. And we knew that from the beginning. So finally, all the setup, again, decreasing, decreasing. Here's what we're going to talk about today. Local extrema. What we're going to do is have an equation, and we're going to try to find the highs and the lows. So in this graph, I'm going to point to it. You're going to tell me, is it a max or is it a min? We're going to say local max, local min for now, because eventually we're going to do something called absolute max, absolute min, the highest max, the lowest max. Right now, they're all called local max or local min. Okay? So I'm going to point to it, and you're going to tell me local max, local min, or neither. Remember, a max is when it goes up, increases, then decreases. That high point is called a max. A minimum is where it decreases, then increases. That low point is called a minimum. And if it increases, neither. Decreases, neither. Okay? So I'm going to point at it. You tell me local max, local min, or neither. So let's look at C1. What would that be? Neither one. Decreasing, then decreasing. C2. Local minimum. Perfect. Why? Decreasing, then increasing, producing a local minimum. C3. Local max. C4. It looks weird, but is it decreasing, then increasing? So it's a local min. And we'll talk about how to find those. C5. Neither. Increasing, increasing. C6. Local max. C7. Neither one. That's all we're doing in chapter 4. Okay? But this is a graph of the original. We're going to find all the highs and lows. Sometimes it will be a max. Sometimes it will be a min. Sometimes it won't be either one. And we'll know because we're going to graph it. Okay? So what things do you need to do for this chapter? Derivatives, algebra, and graphing. It will not be the new stuff. The problems will be with derivatives, with algebra, and with graphing. That's where the problems will come. Okay? So we talked about local max, we talked about local min. Those are called local extrema. And then points where things change. This one just says, if f of c is a local extrema of the function f, then c is a critical number of f. The theorem states that a local extrema can occur only at a critical number. It does not apply to every critical number produces a local extrema. Just because we're going to look at it doesn't mean it will be a max or min. It may be a max or min. Okay? We talked about, they like to use sign charts. Again, if it's decreasing, then increasing the derivative, then it's a minimum. If it's increasing and then decreasing, it's called a maximum. They like to use charts. If it's increasing, then decreasing, going up, and going down, that produces a max. And if it goes up and then up again, that is neither local max nor local min. If it decreases, then decreases again, that is neither local max nor local min. Okay? Where it is a horizontal tangent at x equals c, that's talking about that line. That's the turning point, the critical number. That would be a local min. That would be a local max. That would be neither. That would be neither. Okay? Graphically, that would be a local min. That would be a local max. Neither. Neither. I think we're getting the idea. Okay? So, here's finally all that setup is leading to this. We're going to find the extrema of x cubed minus 6x squared plus 9x plus 1. Okay? We're going to see if it's a local max, is it a local min, and then sketch it. So, I'm going to walk you through this problem step by step. So, take a nice, good sheet of paper. We are starting with f of x equals x cubed minus 6x squared plus 9x plus 1. Okay? So let me be very clear. We're going to try to find the highs and the lows, the maxes, the mins of the original function. How we do that is with the derivative. So what I would like you to do is take the derivative, set it equal to 0 and solve. Look at the derivative, see if there's anything that's undefined. Those will be our points that we're going to look for. You have to know how to get the derivative, and you have to know how to factor. So the issues today are not really going to be with the max and the min. I bet the issues we have today are going to be with derivatives, algebra, and graph. Okay, let's see how we're doing on step 1. Step 1, take the derivative. Derivative of x cubed, 3x squared. Derivative of negative 6x squared, negative 12x. Derivative of 9x, 9. Derivative of 1 is 0. Okay, to find the critical points, the place we need to look at, we take that and set it equal to 0. Dun, 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 and then this is where people get stuck. Now, I'm going to give you 2 ways to do it. Number 1, algebra. What can I factor out of all this? A 3, which leaves you with x squared minus 4x plus 3. Then, this can be factored. If you factor x squared minus 4x plus 3, what do you get? Is it? And you said x minus 3, x minus 1. Factoring, factoring, factoring. Then you set each piece equal to 0 and solve. You get x equals 3. You get x equals 1. Stop there. Stop there. Stop there. Did anybody do it a different way? Nobody found a shortcut? Did what?
I did the same thing, but I didn't take off the 3.
Oh yeah, you could have done it without factoring the 3 first. Yep, you totally could have done that. Anybody else? Surprised. Do you remember that I gave everybody something on your calculator? Does anybody remember that I went around and if you hit program, remember program, quad form, enter, what's A? 3. What's B? What's B? Negative 12. What's C? 9. And if I do quadratic formula, what would I have done for solutions? 1 and 3. There's a shortcut. Okay? But so far, step 1, find the derivative. Step 2, set it equal to 0 and solve. And then I'm going to add a step 3. Look at the derivative. Is there any place where this could be undefined? And what I mean by undefined is dividing by 0. Is there any dividing going on? Is there any x in the denominator? Could this ever be undefined? No. So, again, I'm going slowly. What do we do for these problems? Step 1, find the derivative. Step 2, set the derivative equal to 0 and solve. I now have 2 numbers. Step 3, look at the derivative, see if there's anything that's undefined. Those are going to be things we want to look at too. Questions so far? And then now, let me be clear, all this work is to find the maxes and mins of the original or of the derivative. It's all about the original. It's all about the original. Okay? So step 4, we're going to make a table. So we're going to make a table of the numbers that are important, or the numbers we want to look at. What numbers do we want to look at? Through this process, what numbers did we find? 3 and 1. So 1 and 3. Now, you could use the sign chart, plug into the derivative, see what happens before 1, after 1, in between 1 and 3. But I'm going to do it a different way. You can use the sign chart if you want. I'm just going to go look at it. Okay? So I'm going to go plug 1 and 3 into the original. Into the original. Into the original. Because that's what it's all about. So I'm going to go to my calculator. In Y1, I'm going to put the original. The original is x raised to the 3rd minus 6x squared plus 9x plus 1. Why am I plugging the original into the calculator? Because that's what it's all about. It's all about the original. It's all about the original. Okay? So in Y1, I put the original. I go to the table. I plug in 1. I get a result of 5. I plug in 3. I get a result of 1. What is that telling me? That's telling me where I need to go look. I need to go look at 1, 5, and I need to go look at 3, 1. Are we okay? I'm going to go look at 1, 5, and I'm going to go look at 3, 1 and see what's going on. But here's the downside of my way. If you did their way with a sign chart, you plug into the derivative, see if it's increasing or decreasing between 1 and 3. I'll show it to you before 1, between 1 and 3, and after 3. What I want to do is just look at it. So what I need to do is I need to make a graph. And if I need to see these points, I need to make a window that's appropriate. So if I need to see 1 to 5, 1, 5, I'm maybe going to start with -5 and go to, I don't know, maybe 10. And then I'm going to go from -5 maybe to 10. So you need to come up with a window that will allow me to see those 2 points. And if I go from -5 to 10, let's say counting by ones, and if I go from -5 to 10, counting by ones, will I see all those points and still have enough room? That's going to be the hard part for you, is figuring out the window. So go to window, -5 to 10, counting by ones, -5 to 10, counting by ones. Hit graph, draw it, and then tell me what we have. Okay. Again, we're graphing the original. The points I want to check out are 1, 5, and 3, 1. let's see what we have. At 1, 5, what is this called? A local max. At 3, 1, what do we have? A local min. Those are the steps I'd like you to follow. The only thing we can add a little later is if we had a domain like from this to this, we'll add that as a digit to this. Okay? Now, how does the sign chart fit in? The sign chart fits in by, if you did it the way they have you do it, from 1, 3, those are the critical numbers. If you plugged in numbers less than 1, you'd get into the derivative, you'd get positive results, which means it's increasing. Between 1 and 3, into the derivative, you'd get decreasing, so it went up and went down. Went up, went down, that produces a max. Then it was decreasing, going down, and then if you plug in a number after 3 into the derivative, it's increasing, that produces a what? A minimum. So your choices are sign chart, plug into the derivative, see what happens, or graph the original. I prefer to graph the original, but they have pros and cons. The pros of the sign chart is you just plug into the derivative, see what happens. If it increases, then increases, then decreases, you have a local max. Decreases, then increases, you have a local min. The downside of this way is, yeah, you just have to graph the original in an appropriate window. You have to make a window so you can see those 2 points. You need to make a window so you can see those 2 points. That's the extra work on this one. Okay? That is the section. We're going to do another problem, just talking about it, and then maybe I'll give you one more try. Okay? So again, there's the graph that we got. Come up with an appropriate window, and we find it. So theorem 3 intercepts and extremal polynomial functions is that if a function is a polynomial function of degree greater than 1, then f has at most n x-intercepts and at most n minus 1 local extrema. That gives you kind of a guideline of what to look for. So there's no guarantee that there's nth degree polynomial that has exactly n minus 1 local extrema, but there can be no more than n minus 1 local extrema. Just giving you some guidelines. This we'll just talk our way through. So here, the graph shows the approximate rate of change. Stop there. When it says rate of change, what are they telling us? That's slope of a price of eggs over 70-month period where ET is the price of a dozen eggs in dollars and T is time. So we're going to talk about this. Again, this is not a graph of the original. This is a graph of the derivative. Graph of the derivative. All right? Determine when the price of eggs was rising or falling and sketch a possible graph of ET. So what they're saying is, when was the price of eggs increasing? When was it decreasing? So if I look here, the derivative is negative when it points to the graph and below the horizontal axis. So the price of eggs is falling before and after before month 10 and after month 50. So again, this is the tricky part of this. It's a graph of the derivative. It's a graph of the derivative. So when is the graph negative? When is the graph falling? The price of eggs is falling before month 10 and after month 50. That's when the price is falling. When is the price increasing? When is the price increasing? When it's above 0. So the price is increasing when it's above 0, between 10 and 50. That's when the price is increasing, when it's above 0. So taking that information, at month 10, the price of eggs is at a minimum because ET changes from positive to negative at the 50th month. At month 50, the price of eggs is at a maximum. So if I wanted to talk about this, what the original looks like, A graph of the original will be increasing from 10 to 50. A graph of the original will be decreasing when it's less than 10 and greater than 50. And it will have a minimum at 10 and a maximum at 50. So that is what the graph would look like, the original. So this is kind of looking at it backwards. Okay? So, stopping there for a second, okay? They like to throw in a lot of extra stuff.